Alright guys, so let's talk about a homologous series. And so here are three alkanes, and they are part of a homologous series. And so what we have here is we have C2H6, here we have C3H8, and here we have C4H10. And so one thing about the alkanes is we can produce a generic formula for an alkane as CnH2n plus 2. That's our formula for an alkane. Take the number of carbons, so in this case 2 carbons, then we would have 2 times 2, 4, plus 2, 6. That would be our number of hydrogens. But these are all part of a homologous series, and effectively the difference between each alkane and the next one up in the chain is we're going to add to it a CH2. So if we take a C2H6 and add CH2, it becomes C3H8, and we move up the homologous series. So basically what you're doing is you're taking the two CH3s here, you're splitting them and throwing a CH2 in the middle of them, and that's what we do to get to our propane. And then go to our propane to our butane, we do it again. We split this either here or here, and we add another CH2 inside, and that gives us our butane. And so that's what a homologous series is. So a homologous series differs from one member to the next by the addition of a CH2. And that's what makes them different. By adding a CH2, we'll move to the next member of the homologous series. Here is another example of a homologous series. They don't have to be alkanes. In this case, we have C2H5F. We've substituted a fluorine for a hydrogen. In this case, we have C3H7F. Now, if you look at it, the difference between these two is a C and two H's. These are also members of a homologous series. We need to add a CH2 to move to the next change. We can add another CH2 and move to fluorobutanes. This would be fluoroethane, fluoropropane, fluorobutane would be the next member of the homologous series. So they can be more complicated structures as far as in a homologous series, but they don't have to be. They can be simple. Now let's look at the physical and chemical properties of a homologous series. So chemically, they're going to behave similarly. So chemically, they're going to be similar within a homologous series, and that's because they're pretty similar. So if you go back and we look at the fluoroethane and the fluoropropane, they're really similar. It's just that this chain's a little bit longer. We have an extra CH2 in the middle. But this fluorine group is going to react with things the same way this fluorine group will react with things. And so they're going to be similar chemically. Physically, we're going to face some trends, and the one that you really need to focus on is we want to look at the trends in melting point, boiling point. So our trends in the melting or boiling points for them. So let's go back to the first one we were looking at, the alkanes here. So here we had ethane, and here we have propane, and here we have butane. And so one thing that you need to be able to do is you need to be able to determine which of these substances would have the higher melting point or boiling point, and understand why it has a higher boiling point. And so in the case of these three, we have a low melting point, boiling point over here, and they move towards higher on this end. And so we go from low melting point, boiling points to higher boiling point, melting points. And so you need to understand why. Well, remember, if we're talking about melting and boiling, you're talking about intermolecular forces, and so you need to consider the intermolecular forces at work within these molecules. In a alkane, all we have are CH bonds, and CH bonds are not polar. So these molecules are not polar. There are no dipole-dipole interactions, and there are no hydrogen bonding interactions because the hydrogens are not bonded to nitrogen, oxygen, or fluorine. And so the only forces at work here are van der Waals forces. And you should know that van der Waals forces increase as the molecules get bigger. And so the bigger propane has more van der Waals forces, the bigger butane has more van der Waals forces than the smaller ethane, and therefore it's going to have more attractions, greater forces of attractions. It takes a higher temperature to break those forces of attractions, and so it has a higher melting point and boiling point. Now, the other thing that you're going to need to be able to do is you're going to need to be able to identify a similar trend with functional groups, with the addition of functional groups. Identify similar trends as far as melting points and boiling points is concerned. All right, so here are some functional groups of propane, or some 3-carbon chains that have some kind of a functional group attached. And so here we have propanone, in this case, with the double bonded O in the middle. Here we have 1-propanol, and here we have propanal. Over here is propanoic acid, and finally 1-fluoropropane. And so, since they're all the same number of carbons, we need to look at other things and to determine their melting points and boiling points. And again, we're going to be looking at what kind of intermolecular forces we may have. And so here we have an OH, and an OH, you should know, is going to give us hydrogen bonding, the strongest of all intermolecular forces. We also have an OH here on propanoic acid, so this has hydrogen bonding. The C double bond O's in the propanal, the propanone, are going to give us some dipole-dipole interactions. So those are going to give us dipole-dipole. We also have dipole-dipole on the propanoic acid, so we have a hydrogen bond and dipole-dipole there. And the halogenated, or fluorinated in this case, alkane is going to give us some dipole-dipole as well. And fluorine is going to give us the strongest dipole-dipole. If you go to a different halogen, chlorine, bromine, iodine, you get weaker to almost nothing at all for those. And so in these, which would you expect to have the highest boiling point? What has the strongest intermolecular forces of attraction? Well, you probably should go and guess that the propanoic acid would have the highest, because it has hydrogen bonding and dipole-dipole on that C double bond O there. So that would probably have our highest boiling point. And then what would be our next highest boiling point? Well, if we're looking at them, what's next highest would be the hydrogen bonding and the alcohol. That would be our second highest boiling point. And then our propanone and propanal and fluoropropane all are exhibiting dipole-dipoles. And so those might be hard to differentiate one from the other. However, you're probably going to have a little bit higher in propanal than propanone. So we'll do that one fourth. And this one's just kind of hard to tell because it depends on what the identity of this is. Fluorine is going to be a pretty strong one, and so this might actually be more polar than propanal, and that might be third, and that would push us to fourth and fifth. But if this is, say, iodine, then it would probably be the fifth one in the order, because it depends on what the identity of this halogen is. And so the reason why we'd probably put propanal before propanone, and propanal, the C double bond O is at the end of the chain, and therefore it has a little more exposure, if you will, to other molecules, versus the propanone, the O is in the middle of the chain, so it might be a little less exposed to other molecules to interact with. And so I'd probably put propanal slightly above propanone as far as the strength of their intermolecular forces, but they're really, really close. All right, and let's look at one more situation. And so here we have 3 isomers. These are going to be isomers of pentane. So they're all C5H12, C5H12, and C5H12. So we have straight chain pentane, we have 2,2-dimethyl propane, and we have 2-methyl-butane. And so would the boiling points of these be the same, or would they be different? They are all nonpolar, so they're not going to have anything other than van der Waals forces, because there's no OH or anything like that in here. But they're not going to have the same boiling points. They are going to be different. And so which would be higher, which would be lower? And so in this case, pentane is going to have the highest boiling point. The straight chain pentane will have the highest, and the 2,2-dimethyl propane is going to have the lowest boiling point. And the reason being is that because we've started to branch this thing out, the more branching we have, the more compact the molecule becomes. And the more compact the molecule becomes, the less surface area is available to make hydrogen bonding with other molecules. In this case, we have much more surface area available to hydrogen bond with other molecules. In this case, we just have less surface area available. And so the 2-methyl butane is going to be in the middle. It's going to have the middle boiling point, if you will. It doesn't have as much surface area as the pentane, but it's got more surface area than the 2,2-dimethyl propane. And so your simple rule there is more branching equals lower boiling point. More branching equals lower boiling point and melting point, any of those. And so just the physical and chemical traits and trends for homologous series and looking at different structural isomers and looking at different functional groups. You need to be aware and be able to apply and use the differences here to determine differences in boiling points and melting points.